Hi, my name is Ching and welcome back to Data Structures in C++. In the previous lectures, we have been mostly focusing on C++ fundamentals, including pointers, arrays, and classes. We also demonstrated on how to use Visual Studio Code to create, build, and debug your C++ project. I hope that gives you the minimum preparation to write code about data structures. But before we jump into data structures, we need to learn one more thing. That's what I'm going to talk about today. Today's topics will help us understand the reasons behind the design of various data structures and the algorithms to implement those. To understand that, I will first introduce asymptotic analysis. Then I will use the big O notation to describe the asymptotic behavior of code. Instead of strict theoretical proofs, I will use examples to show you how to calculate the complexities for given codes or algorithms. At the end, I will summarize some of the most common complexities in a table. Before we start to learn various data structures, the fundamental question is how and why are those invented in the first place? We understand data structures will make our program run faster. But how do you know it's actually faster? Or more specifically, if given multiple choices of data structures or algorithms, how do you tell which one is faster? The question can become even more complicated if you consider different hardware configurations, such as different types of CPU, memory, or even hard disk. Nowadays, the computer program can even run across multiple computers through networks, such as in cloud. So how do you predict the performance? That's only one dimension of the problem. The other dimension comes from the different characteristics of data sets. How big is the data set? What are the types of data? How are they distributed? How are they organized? How frequently are they updated? With so many factors, obviously it will be very expensive or impossible to just try them one by one and compare the performance numbers. Like any other sciences, we need to find a way to analyze them mathematically before we roll up our sleeves and get our hands dirty. With the right mathematical tools, our goal is to guide the design of better data structures and algorithms so that the program can scale efficiently. To understand how a big problem is, let's first start by defining the size of a problem. It seems to be quite simple. You just need a few variables to describe it. Here are some examples. If you are working with a one-dimensional array which contains n elements, for example, finding the maximum value, then the size of the problem may be n. Following this line, if you're working with 2D matrices, you could use the number of rows m and the number of columns n to describe the size of the problem. But more often, the size of the problem doesn't mean the size of the data. For example, finding the largest m elements from an array of size n. In this case, there are two variables used to describe the size of the problem, m and n. Even though n is the size of the dataset, the solution has the size of m. Because we don't really worry about performance when the size of a problem is small. What we really care is what's the expected behavior when the size of the problem is becoming big enough. This type of analysis is called asymptotic analysis. The idea is when the size of a problem is big enough, we want to know the trend of how it grows. Let's start with an example. We compare these two functions, fn and gn. Fn is just n squared, while gn is n squared minus 3n plus 2. If we plot these two functions out in this diagram, At the very beginning, we see a big difference between them. But if n becomes big enough, there's not much of a difference between the two curves. In other words, their trends are the same. Remember, what we really care about is the trend of growth. When n becomes big enough and continues growing, what kind of computing resources do we need to keep up with the pace of its growth? So only the most dominant term matters. In this case, it's n squared. Here's another example of what we just explained. Fn is n to the power of 6, while gn is n to the power of 6, with a lot of other less powerful terms following it. If we plot these two functions out, at the very beginning they look very different. But if n becomes big enough, they follow the same trend. Here's only the most dominant term, n to the power of 6, matters. Now we know how to only keep track of the most dominant term. But how do we represent it mathematically? Here we introduce the big O notation. Let's look at an example. How do we find the maximum value from an int array? Here, this function passes in the array as a pointer and the size of it. First, you take the first element of the array and assign it to max. Then we loop through every element and check if it's bigger than max. If so, we assign the element to max and continue. This loop will run n-1 times since we already assigned the first element of the array to max. Every time we enter the loop, we do a couple of things. We first get the element at the current index I. Then we make a comparison with the max value. If that's true, then we assign the current element to max. The code inside the for loop takes 4 operations in all. These are also called primitive operations, and they all run in constant time. So we can say that this algorithm runs in the order of n. Mathematically, we use the big O notation to describe it. We represent this as O parentheses n, or we simply call it On. This is also called the linear runtime complexity. You might have noticed the complexity mostly comes from a for loop. Let's formulate this a little bit. First, let's assume the initialization, condition, and increment all run in the constant time, O1. So we will focus on what's inside the body of a for loop. An easy scenario is that the body has the same complexity for each cycle of the loop. Or in other words, Fm is independent of the variable I. So the total number of operations are simply to run the body n times. That's the nfm part, plus n times of the other constant operations. That's the n part. We know Fm must be at least O1, so nfm is the most dominant term, where that the final complexity is in the order of n times fm, or in the big O notation, ONFM. Here is a more concrete example. It is a nested loop with the inner loop looping m times to add up the variable j. So the inner loop has the complexity of OM. The outer loop loops n times. Thus, the total complexity is in the order of n times m. But sometimes the loop body has its size dependent on the outer loop variables. For example, if the body runs in the order of a function depending on I and n, we use a function f with parameters I and n to describe its complexity, or the number of operations. Now for each I, the body will run different number of operations. The total number of operations will be a summation of all possible I values from 0 to n-1. together with n times of other constant operations, we get this final formula for total complexity. We may be able to simplify it if we know what the function f is. Let's run another example to illustrate the scenario. Now the inner loop depends on the variable I, or more specifically, the inner loop loops I times. So for each I value, the complexity of the inner loop is OI, using the formula we got from the last slide. So we have the total complexity as in the order of n plus a summation of I, where I is from 0 to n minus 1. Let's expand and calculate this summation. By keeping the most dominant term n to n squared and skipping the constant factor, we can simplify the big O notation to O n squared. But how do we calculate other summations, such as the summations of I squared or I cubed, etc.? Here's the list of summations with the powers from 0 to 6. Actually, there's a formula to calculate the summation for any given power, but it still looks way too complicated. The good news is, in asymptotic analysis, we only care about the most dominant term. So what you really need is the following big O formula. It basically says we can simply replace the variable I with n. Then the summation becomes n times of n to the power of a. And the result is just n to the power of a plus 1. We will use this trick in the next example. In this example, we will start from the loop body of the innermost loop and work our way out. The body runs in constant time. Repeat with j times, this loop runs in oj time. Then sum oj for I times when j starts from 0 to I minus 1. It's the equivalent of the sum oi for I times, which is simply oi squared. Then for the outermost loop, we sum oi squared for n times where I starts from 0 to n minus 1. That's equivalent of the sum n squared for n times. So the final complexity is n times o n squared, which is o n cubed. So far, we've talked about a few different categories of complexities, such as the constant time, O1, linear complexity, ON, and polynomial complexities, O n squared, O n cubed, etc. There's another category of complexities called the logarithmic complexity. The logarithmic complexity is basically saying, how many times can you half the problem until the size becomes 1? So if you have a problem with a size n, for every step, you reduce the problem size by 2. Then you will need log n steps to solve the problem. That leaves you with an O log n complexity. For example, if n is 16, we can half the problem by 4 times. The logarithmic complexity is best illustrated by a binary search algorithm. In this example, we want to find the value of 37 in the sorted array. The upper solution is the binary search. At each step, it tries to reduce the problem size by half by checking the middle value of the rest numbers. The bottom solution is just a sequential search, which runs in a linear runtime complexity. We also mentioned at the beginning of this lecture that the performance also depends on the data. In the next 2 slides, we will show the worst case scenario and the best case scenario. In the worst case scenario, we search for 1. The binary search takes 4 steps, which is log n as we have predicted. The bottom solution is just lucky to find it on its first try. If we search for 23, then we have the best case scenario for the binary search, because 23 just happens to be the middle value of this array. The sequential search still has to go through every element. By analyzing the best, worst, and average case scenarios, we have a more complete idea on the performance of an algorithm in various conditions. In summary, we talked about some typical complexities: the constant, logarithmic, linear, quadratic, cubic, etc. It's also common to have some of those terms combined. Here's a table of typical complexities from fastest to slowest. First, there is constant time complexity, which is O(n). This is the best possible complexity. The logarithmic complexity is the next. It is pretty close to the constant time, since log n is still a small number with a very big n. We can also have two nested loops with logarithmic complexity each. Thus, we got a log squared complexity. Then we have the linear complexity, which grows linearly with the problem size. If the algorithm has two nested loops, with one loop linear and the other logarithmic, we get an n log n complexity. After that, we have the quadratic and cubic complexities, or any higher power complexities. These are also called polynomial complexities. Finally, we have the exponential complexities. These are extremely expensive and usually mean the problem has no practical solution except for the very small size. And those problems are often the most difficult problems in computer science. This concludes today's lecture. Have fun and happy coding. I'll see you next time.